Start.
Okay, so welcome everyone. Today we will demonstrate about Thyristorized control fully converter. Okay, so as we see in lecture notes, what we see this circuit diagram for a fully controlled thyristor converter, in which we have just applied input side a AC source, and we apply a gate pulse to various thyristors. Okay, according to gate pulse we can get a voltage across the load terminal. Here in this practical we will connect a R load, as well as we also studied a output waveform with RL load. Okay, so here we have a various motors. Okay, like a separately excited DC motor as well as PMDC motors. Okay, so we just connect a DC motor across load and plot a various curve, and if we can change a duty cycle or a firing angle to a various gate pulse, then we can regulate the speed of DC motor. Okay, so this is one a small application of this converter to control a DC drive. Okay, so now come to a hardware setup. Here input side is our power supply. So input single phase AC is given to our controlled circuit or converter circuit. In this converter circuit we have T1, T2, T3 and T4 for SCR. Okay, and 4 ACR connected as our circuit diagram, and output is connected to the various types of load. And the control circuit is responsible to give a firing to various switches, and here this block is shown here give a firing for our converter. So in this circuit you see here, first we need to detect a zero crossing, then we can generate a ramp signal. So we can generate a short-tooth waveform from ramp generator, and whenever zero crossing is occur from a AC sinusoidal input, zero ramp generator will again reset. So we can get a short-tooth waveform. Again short-tooth waveform will compare with a comparator through this variable port. Okay, and if you vary this variable port or control signal, VC signal is providing by this knob. So by human or by open loop control, you just set a control signal from this knob. We can control a firing delay across the output across the ramp comparator. Again, this comparator, the signal is a low voltage signal, but we required a amplify or convert this high voltage due to the requirement of a power switches. So and another one, the isolation is very important to for a lower side and high voltage side. So we need a pulse transformer to to provide a high voltage isolation between a high and low voltage side. From output of pulse transformer we get a various pulse, so that we get a G1, G2, G3, G4 is a 4 gate pulses for a 4 switches. So we connected according to our circuit diagram that pulses, and again for a measurement section, if you see here, we can measure from this kit the output DC voltage as well as DC ampere current. Similarly, input voltage and input current. Okay. Another one, we can also analyze the waveforms from a DSO, and this waveform can be stored or captured from our power system or PC system. Okay. Now just open our setup to see how the circuit is working or perform its working. So now I just trigger or on the power supply. So we get a blinking the LED over here, power supply LED, and now input voltage I just apply before open my load and connect the input. So as you see here, the output, this is the output voltage waveform. Okay, and this voltage is nothing but first one is 200 volt, have a scale is there. Okay, so 200 volt means 200, and approximately it is 315. Okay, so RMS voltage is 230 approximately of this waveform. Now this input voltage, and this is waveform for a output. Now I am not applying any gate pulse. So if you vary the gate pulse from this knob, we can get a output voltage across the load. Okay, here we not connected any load, so the current is not flow in the circuit. So we need to first connect the load. So I just connecting a R load. Now my firing is approximately about 180 degree. So I just decrease my firing angle from this knob. Now you see here I set a firing pulse approximately 160 degrees, so I get a small pulse, okay, at output side. And output voltage you see here 17 or 18 volt. So we get 18 volt DC output, as well as current is 0.12 ampere DC current is flow through the bulb. As well as input voltage is showing, this is the RMS voltage, this is constant 244, and input current is depend on how you can give a firing to that circuit. Now I just increase my firing for a R load. Now approximately we trigger the firing about 90 degree. Okay, so as I trigger a 90 degree firing, so I get a waveform like that. As I on my current probe to measure the current. So if you see here, this is okay. So as I increase my firing to about 90 degree, then I get a voltage, DC average voltage is 103 volt. Okay, as well as current is also increasing. So now if you see waveforms, so you can see this is yellow one is our input voltage, and now I fire a 90 degree firing, so that half pulse of input is reflected across the output voltage. As well as the switch is on, the current is flow through that switch and R load, so I get a waveform like very similar with a current and waveform, current and voltage are both are same. So if you can, we can understand that if I change again a firing about 10 degree or 0, approximately 0, I can see there we can get a very uncontrolled rectifier output voltage like diode rectifier output. Okay, so what is the conclusion? If we can change a firing, we can get output voltage across a variable output DC voltage. Now I just connect a DC motor across the load terminal and see how this current will reflected. Okay, so I just connected. Okay, so now I connected a PMDC motor with 200 watt power and 200 volt DC input terminal, maximum input DC terminal voltage across the motor. We can apply 200 volt. Similarly, at a rated torque, a rated load, the motor will take a maximum 1.2 ampere current, as well as the RPM of the motor is 2000 RPM. So this is the combination with attached with a tacho generator. Okay, so here the tacho generator is connected below the shaft, and we get approximately output across the from the tachometer we convert the speed RPM into DC voltage, and this RPM can be generated in a voltage. So we get a 10 volt at 1000 RPM. Okay, so we can scale or calibrate that RPM in the terms of calibrate the voltage in the terms of speed. So now I connected the load, and as everything I connected, the firing is connected. Now I just apply the gate pulse to first circuit. So I just on my gate pulse power supply. Again I also on my input supply. So here now the firing or control signal is 0, so that we not get any current or voltage over here, as well as speed of motor is also 0. Now I just increase my firing angle. So as you see here, we get a very current waveform. Due to this current is this voltage is going negative because we have a RLE load. Okay. Similarly, if the here you can see we get a 10 volt. So motor wheel is rotating at a approximately 1000 rpm. Okay. Now I increase my firing. So current as well as voltage both are increasing. So I get again a waveform like that. Okay. So as if you increase the current, increase the firing, motor will rotate its full speed. Okay. As well as if you apply a load through this pulley, we can see the back EMF is reduced as well as speed is also reduced, so that current is increased. Okay. So similarly, we can conclude this practical that from the control signal or firing, we can control a motor speed RPM. Okay. So I conclude here, we can control the speed of a DC motor using single phase fully thyristorized converter. Okay. Thank you very much.